I'm Bill Kinney, and this is my fourth video about multivariable calculus challenge problems. In this video, we're going to look at a combination of problems 80 and 81 from section 11.1 of the calculus book by Rogawski and Adams, 3rd edition. It's about a famous curve called the Folium of Descartes. It's a curve that has this defining equation. This is a cubic equation in x and y. This is called a cubic curve, this blue curve that you see here, where a not equal to 0 is a constant. This particular blue curve that you see down in this picture is the situation where a equals 1. Okay, that's what we're looking at when we look at that diagram. We've got a part A, B, C, and D. Part A says to show that this line y equals t times x, which would be a line to the origin with a slope of t, intersects the folium at the origin and at one other point P, at least when t is not equal to -1 or 0. Also express the coordinates of that point P in terms of t to obtain a parameterization of the folium. That makes this folium relatively easy to analyze because we can come up with this parameterization. And if you didn't know what it looked like ahead of time, trying to guess something like this to help you hopefully come up with a parameterization would be the best approach to trying to draw it as well. Indicate the direction of the parameterization on the graph. In other words, as t, the parameter increases, what is the direction of motion that generates the curve? That's part A. Part B, describe the interval of t values parametrizing the parts of the curve in quadrants 1, 2, and 4 like you see here. Actually, that's when a is positive. When a is negative, it's quadrants 2, 3, and 4 instead of 1, 2, and 4. But we'll do it with assuming a is positive. Note that t equals -1 is a point of discontinuity. Part C, calculate the slope, that's dy dx, not dy dt or dx dt, the slope dy dx as a function of t. That's a little strange. Well, it's because we're going to use the parameterizations. Find the points where you have a horizontal or vertical tangent, where dy dx is 0 for horizontal or undefined, infinity if you prefer, for a vertical tangent. Part D, show that the asymptote of the folium is the line x plus y equals -a, which is the line that you see right here in red. That, by the way, is equivalent to y equals -x minus a slope of -1, and a vertical intercept of -a. So again, this is the picture when a is 1, so the intercept is -1. All right, I think we can kind of talk about parts A and B at the same time here. As I do some algebra, I will also be describing what's going on in the picture. So this is really A and B. I'm not going to write out an explanation for B, but I'll just verbally describe it. And by the way, I am doing something differently here in this video than I've done in the first 3 videos. At this point, we've typically gone to Mathematica and made an animation to help us understand what was going on. I am still going to do that here, but I'm going to wait for the end of the video to do that. In this first part, we're going to just think about it with our minds and try to draw it based on this picture, which is definitely a good skill to have, especially if you don't have the technology. So, the key is this equation here, y equals tx, is a line with that goes to the origin with a slope of t. For fixed t, say equal to a large negative number like -100 or something, the line would look about like this. It would look close to vertical, but with a negative slope, go through the origin. It's going to certainly touch the folium at the origin, but it's also going to intersect it at some point right about there. Okay, the line, I won't actually draw it, but it would look something like this. Intersect the curve at the origin and also one more point. And as t increases from that large negative number, like -100, the line is going to look more and more like this. Still going through the origin, but now the slope gets closer to 0. The intersection point moves down this way. So this is supposed to indicate that it seems clear when t is a large negative number that we definitely have one other point of intersection besides the origin. And as t approaches -1, the line looks more and more like that red line. And when t equals -1, evidently, it's parallel to the red line, and it looks like there's no other point of intersection. On the other hand, when t is bigger than -1, but still less than 0, the line looks about like this. There's going to be one other point of intersection over here. As t continues to increase towards 0 and the slope of this line increases towards 0, the intersection point moves toward the origin. When t is 0, the line y equals tx is the same as the x-axis here, and there's only one point of intersection at t equals 0. That's at the origin. Then when t is positive, the intersection point moves along this part of the curve, and as t continues to increase toward infinity and the slope increases toward infinity, the intersection point moves this way and heads toward the origin as t goes to infinity. So I've now just verbally described really how to answer part B. The direction of parametrization is going to be this way, and you're going to be in the fourth quadrant, at least when a is positive, when t is less than -1. When t increases from minus infinity, so to speak, up to -1, but not equal to -1, we head off this way. When t equals -1, it's undefined. And when t is bigger than -1, but less than 0, we are heading this direction. So we're in quadrant 2. When t equals 0, we're at the origin. When t is bigger than 0, that's when this part gets parametrized. So evidently the fastest part of the motion for the parametrization must be down in the fourth and second quadrants. The velocity vectors must be very long, and then the slowest part of the motion would be in quadrant 1. It's also going to be slow motion in either case when you're close to the origin, up here or down there. All right, so now let's actually do the algebra to come up with the parameterization. It's not a guarantee that it's going to work, but it does work out pretty nicely in this case. And this is, if you, again, didn't have this picture and you were trying to graph this, you might hope something like this would work. And it does give you parametric equations, which would be the best way to try to graph it by hand if you had just minimal technology, like no graphing calculator, but maybe a calculator itself. So we can just do substitution. We can replace, anytime we see a y in this equation, we can replace it with t times x. And we are going to get a cubic equation in x, which in general could be difficult to solve, but in this case is not too hard because we can easily factor it. Let's see, the cube term is going to be 1 plus t cubed in parentheses times x cubed. And then we're going to have a minus an x squared term is going to be minus 3a tx squared, and no other terms, no constant term, no linear term. This is the equation we want to solve. Because there's no constant or linear term, we can factor out an x squared and write it like this. And this equation for fixed t has two solutions, x equals 0, and what you get when you set this equal to 0, which would give x equal to 3at divided by 1 plus t cubed. So as long as t is not equal to -1, we can do this, and we do get this other solution. And then we can use this equation again, y equals t times x, to solve for y. Just multiply this by t to get 3at squared up top now, divided by 1 plus t cubed. So these two equations as a pair form the parameterization of the Folium of Descartes as long as t is not -1. When t is 0, they coincide with the origin, just like the other solution of this being x equals 0. You only have one solution then when t is 0, but when t is non-zero and not -1, then you have two distinct solutions to this equation and therefore two distinct points of intersection, and this is the one we're more interested in. All right, so we've essentially now done parts A and B. On to part C. Calculate dy dx, the slope of the curve, as a function of t. Find the points with horizontal or vertical tangents. We can use the equation that we've used before. Dy dx, the slope, can be found as a ratio of dy dt and dx dt. Okay, this is not a justification, but intuitively you can imagine canceling the dt's to see that. That's definitely not a full justification. You really need the chain rule to justify this more fully, but we are accepting this. So we got to find dy dt and dx dt. That's a little bit of a pain here because we've got fractions. We've got to use the quotient rule. Look at this equation for dy dt. Let's see, I remember it as low d high, meaning the derivative of the top, which is 6at minus high 3at squared. D low is the derivative of the bottom, 3t squared, all over the square of what's below, 1 plus t cubed quantity squared. Similar kind of thing for the derivative of x with respect to t, and ultimately the 1 plus t cubed quantity squareds will cancel. Let's see, I'd have low d high minus high d low over the square of what's below. And I'm just using the quotient rule there. Maybe you did not memorize it that way. Cancel the 1 plus t cubed quantity squareds. All the a's can go away, by the way. All these a's, there's one a in each of these terms. They can be canceled. And ultimately, what will we be left with? Let's multiply the, well, I can cancel 3's as well, one of the 3's in each of these factors. Here we'd be left with a 2t, cancel the a, times 1 plus t cubed. That'll be 2t plus 2t to the 4th. And then here we cancel the a and one of the 3's. We get a minus 3t to the 4th. All over. Here the 3a canceled, leaving you with 1 plus t cubed. 3a canceled there, giving you minus 3t cubed. Simplify a little more. Can factor out a t on the top. T times 2 minus t cubed. On the bottom, we can just write it as 1 minus 2t cubed. Okay? So that's dy dx as a function of t. But now we also want to find the points with horizontal or vertical tangents. We're going to have a horizontal tangent where the numerator of dy dx is 0. We're making dy dx itself 0. So t times 2 minus t cubed equals 0. T equals 0 or cube root of 2. Let me quickly just estimate the cube root of 2. Turns out to be about 1.26. That's going to be here and here, where you've got horizontal tangents. This one when t is 0. This one when t is cube root of 2. To find the x and y coordinates, which I will not bother doing, you could plug t equals cube root of 2 into here and here. You get it in terms of a. When a is 1, you could plug in a equals 1 as well to find the particular coordinates. I won't take the time to do that. And you're going to have a vertical tangent. By the way, my students, if I assign this problem, you should do that. For a vertical tangent, it's going to be where dy dx is undefined, where I'm dividing by 0, as long as it's not at the same value of t, where the top is 0. So set the bottom equal to 0 and solve for t, and you're going to get t is 1 over the cube root of 2, which turns out to be about 0.79. Right there, t is 1 over the cube root of 2. You might say, well, what about here at the origin? Don't we have a vertical tangent there as well as a horizontal tangent? Yeah, well, though only when t is infinity, so to speak. It's best just to think of it as a horizontal tangent when t is 0, because as t goes to plus or minus infinity, we only approach the origin and we never reach it actually with this parameterization, though you could say the curve itself does have a vertical tangent there. I'll go ahead and write that t is plus or minus infinity, even though that's not a number. Hopefully you know what I mean. All right, what about part D? Show that the asymptote of the folium is this, which happens as t approaches -1. That's important to realize here. So we need to really take a limit as t approaches -1 of what? Well, maybe the value of x plus y. If we can show that limit is -a, then we'd be done. That would mean this would be an asymptote. So we've got to plug in these two things, get x and y in terms of t, take a limit as t goes to infinity. They already have a common denominator, so I can just add the numerators. I got 3at plus 3at squared all over 1 plus t cubed. This, I keep writing infinity, -1. As t approaches -1, both the top and the bottom go to 0. -1 cubed is -1. 1 plus -1 is 0. Here we get a -3a, and here we get a +3a. This is a 0 over 0 indeterminate form. It's a situation where we use L'Hopital's rule. Some people spell L'Hopital with an S in there, and that might be the better way to do it, but I'm going to go ahead and just write it like that. L'Hopital's rule. We need to differentiate the top and the bottom individually. It's not the quotient rule. Differentiate this and get 3a plus 6at. Differentiate this and get 3t squared. And now this is not an indeterminate form as t goes to -1. We're not dividing by 0. We get 3a minus 6a is -3a. Divided by -1 squared is +1. And we do indeed get -a. So the value of x plus y for this parameterization, which is generating this curve, approaches -a as t approaches -1. And that means this line, x plus y equals -a, is indeed an asymptote, like we see here. All right, now we're going to go to the Mathematica. All right, now we're at our Mathematica notebook where we can look at how the graph was made and animate it. So this is code that generates the graph that we saw on the piece of paper. There we go, there's the Folium of Descartes. And here's the code if you're interested. Let's now make the more interesting thing, the animation with manipulate. So we can watch this curve get traced out. There we see the line t, with line through the origin with slope t in green here, and we can play that. A is set to +1 here. As we play that, we see the green line started with a large negative slope. Then the slope increases towards 0, equals 0 for an instant, then becomes positive, and you see the intersection point. For example, when t is about -2.6, the intersection point is right around there. Moves along the curve. When t is -1, right about close to here. The red and green are supposed to be parallel, and there would be no intersection point. When t is bigger than -1, there's an intersection point in the upper left in quadrant 2. T continues to increase through 0. The intersection point moves into the first quadrant, and then as t continues toward infinity, now this intersection point is heading back down toward the origin. Okay. You can get Mathematica to do some solving for you, to solve for the parametric equations if you like. We can also make add some velocity and acceleration vectors to the picture just for fun. I made the asymptote extra boldface here, so we're going to see something interesting. We're going to see Mathematica draw in the asymptote here as t varies, which is technically not part of the graph, but we won't worry about it. It's not doing the greatest job with the animation. I added some arrows to the picture. You can barely see them here. The orangish arrow right about there is the velocity vector. There's a magenta colored arrow as well. It's difficult to see. The orange one points tangent to the curve, and its length is the speed. The magenta one is the acceleration vector, the derivative of the orange one. It's practically pointing in the same direction. That means the object is speeding up as we go there. I know those vectors are difficult to see. Now as t increases past -1, we come back over this way, and now these vectors get easier to see. So again, I guess I had it the wrong way around. Sorry about that. The magenta one is the velocity vector, and the orange one is the acceleration vector. Now the angle between them is large. That sort of means the acceleration is causing the velocity vector to get shorter. That's not literally what's happening, but it's a nice imagination tool. Now they're getting really short because the motion is very slow as we head back toward the origin as t goes to infinity. Okay, so that's kind of fun. We can make plots of these things individually as well. I'll let you think about these. Okay, the graphs of x, y, x plus y, and -a, which is important when t approaches -1. I'll let you think about what's going on there without describing it. We can also simplify the ratio dy dt divided by dx dt. Mathematica can do lots of neat things. I can also change the value of a, by the way, and get different foliums, including if a is negative, it goes back this way. Okay, so hope you enjoy learning about the Folium of Descartes.